Okay, back again. We'll be focusing in for the next couple lectures on minerals specifically, as we discussed in class. This particular lecture segment will accompany page 355 to 358 from your handy, yet slightly out-of-date textbook. So make sure, again, I'm going to encourage you guys to keep up with the reading. All right, so we talked a little bit in class today about what minerals actually are. Textbook definition: they are elements or compounds of elements that occur naturally in Earth's crust. Examples: salt. All of our metals are minerals. Quartz is a mineral, common in rocks. Okay, and as I mentioned, when we talk about rocks are just simply mixtures of various minerals. All right, so like granite and basalt have a variety of minerals that make up those rocks themselves. So what are some of our more abundant minerals? So things that we can rely on and use widely. All right, silicon dioxide, which is the raw material for making glass. All right, there's a lot to do about recycling glass and not trying to use so many raw materials. Not that that's not a valid argument, it's just that silicon dioxide is the most abundant material in the Earth's crust, right? And so we've got a lot of it, and so it's not like we're going to run out of silicon dioxide. And in fact, if glass ends up in a landfill and we feel like we don't want to go use raw materials for glass, we just go dig in a landfill and find some more glass. It's all over the place, okay? Other abundant minerals are aluminum and iron, although not nearly as abundant as silicon dioxide, and much more energy intensive to get from raw materials. So as we saw in the little recycling and aluminum exercise today, even though there's a lot of aluminum still in the ground, it's much more energy efficient to recycle that aluminum. Same thing goes with iron and steel, etc. All right, so some scarcer minerals in the crust that we still rely on. Copper and chromium. Copper, of course, we know used for wiring electronics. Chromium is an important additive to steel when we need to make sure that it's not going to rust. And molybdenum is used in electronics and several other things as well. And those are what we call scarce minerals. They're not ultra scarce, they're just not nearly as abundant as aluminum and iron. All right? And then our minerals are just not evenly distributed, right? They come in little pockets. Now, I guess you could say that we can find traces of all kinds of minerals really anywhere, but we're looking for places where those minerals have concentrated themselves, okay, into these ores. So a mineral ore is referring to a mineral compound containing a relatively high percentage of a particular mineral resource. One example is the mineral bauxite, which is the ore we use to obtain aluminum. All right, and then our ores themselves, even though they do have a higher than normal concentration, we still separate those into what we call high-grade ores and low-grade ores. So high-grade ores contain an especially high percentage of the mineral resource. So those are our gold standard, if you will. Get it? Gold standard mineral. Come on. Anyway, assaying. So assaying is the process by which we determine just how much of a particular mineral we can get out of an ore. Okay? So when mineral deposits are found, or certain ores are found, the assay process is done to identify whether it's a high-grade or low-grade ore. So it gives us a method for determining the percentage of ore that is actually the pure metal. So if we have, again, we can go back to bauxite. If we have a high-grade bauxite ore, or even a low-grade, we can use it through the assay process to determine just what percentage of that ore is the metal we're going after, and then we can make a prediction about how much we should get, how much profit we can make, and so on. All right, so geochemists typically would be hired before opening a mine to kind of determine how profitable it might be to mine in a particular area. And in fact, one of the labs will do sort of a mock assay process on a copper compound to determine how much copper we think we might be able to get out of it. Okay? So how is it that mineral deposits form, right? And then how can we use that information to help discover where mineral deposits are or might be. All right. So there are natural processes, obviously, that produce mineral deposits. And again, when I say mineral deposits, I'm talking about those locations where we have an especially high amount of a particular mineral. All right. One of the ways we get little pockets of minerals is through what's called magmatic concentration. So we have magma underground, which is molten rocks and minerals. And when magma is allowed to cool off slowly, what happens, so rather than like when it erupts at the surface and it cools off rapidly, everything kind of just intermingles in a homogeneous distribution. When magma is allowed to cool off slowly, there are different melting points for different minerals, right? And so as the magma cools, the heavier elements like iron and magnesium settle out and get concentrated in certain locations. And so magmatic concentration is responsible for most of our iron, copper, nickel, chromium, and magnesium deposits. All right. Hydrothermal processes. So you've got really hot water in our hydrothermal vents. It also tends to be fairly acidic. All right, which allows it to dissolve certain minerals. And when hydrothermal vents kind of spit this hot mineral-rich water out, it creates these deposits on the seafloor, and things like gold, silver, copper, lead, and zinc end up being deposited in that way. All right. Another process is, let's say we have a mineral deposit. Over time, when these get exposed to the surface, erosion, wind and water erosion can erode the sediments containing these minerals away. They can get deposited on the seafloor or even in rivers and streams. Okay, and because things like iron and manganese, etc., have various densities, sometimes they tend to settle out differently. And so when you see people with the like called gold panning, for example, they're taking the sediments on the bottom of the river, and because gold is super dense, they can kind of use some little tricks using water and so on to separate little pieces of gold out from other lighter sediments. Okay, so sedimentation, we can get iron, manganese, phosphorus, sulfur, and copper, right? And then evaporation can cause non-metallic minerals that are water soluble. So things like borax and salts and gypsum are left behind that we use for a variety of purposes. All right, so these are the 5 main methods by which minerals will aggregate into high concentrations in specific areas. Again, keep in mind, if you were to pick up a handful of sediments, you might find really, really small trace amounts of darn near everything. Okay, but we're looking for high concentrations of one particular mineral when we're getting ready to mine an area. Okay, so how do we go about figuring out where these mineral deposits are? How does a mining company know to drill down hundreds of feet in a particular area? All right, there are a variety of techniques. So they might use like aerial or satellite photography looking for particular formations. And so, for example, when they're drilling for oil, one of the places they look for oil is in like little dome-shaped structural traps. And that's easier to see from aerial photography. Aircraft and satellite instruments can measure the Earth's magnetic field, so things like iron, which are ferromagnetic, right, have a different sort of magnetic field. And also seismographs, they can measure differences in how seismic waves travel through different materials, and that gives them clues where certain types of materials might be found. So those are some methods, and what they do is they essentially combine those methods with the knowledge of how minerals are formed. So like the magmatic concentration or sedimentation, etc. So they kind of combine those things together. And this is really the importance of geologists within the field of mining. They are really important with the discovery of where minerals might be. Okay? That's it for now. On Monday, most likely, when you guys walk in, we'll do a little lab. Actually, it's a 2-day lab extracting copper from a copper compound. So you will do a little single replacement reaction to do that. But make sure you guys get the reading, walk in with the notes, etc., so that we can charge ahead. All right. Have a good weekend.